Okay, so let's go ahead and let's start with our midterm review. All right, so we are going to talk about a little bit of each topic that we've gone over the first half of the semester. So we're going to talk about SMAW. We're going to be talking about joints, positions, and weld symbols. We're also going to be talking about gas metal arc welding, and we're going to be talking about metallurgy. So while you were going through the modules, there was a lot of information on each one of these topics. And in the book, it goes even more in depth. So what I'm going to do for the midterm is I'm just going to give you the meat and potatoes, so to speak, just the things that you might be tested on. You won't be tested on each subcategory for each topic, but there are going to be a few questions from each topic. So I'm going to go over a little bit of everything, just the topics that I really want you to focus on, and we'll go from there. So the first topic we're going to begin with is shielded metal arc welding, or SMAW for short. So SMAW. Now the topics that we're going to be covering for SMAW are going to be power source, polarity, duty cycle, electrode classification, and the 5 essentials. So when we're using shielded metal arc welding, it's important to know the type of power source that we're using. It's important to know the polarity that we're using. Depending on the machine and the type of work we're doing, it's going to be crucial to know the duty cycle of our machine. We're going to need to know how to decipher the classifications of our electrodes. That way we know we're using the correct electrode. And then the 5 essentials. So let's go ahead and let's start with our power source. Now with shielded metal arc welding, it is a manual welding process. This basically means that we, the welder, feed the electrode into the weld puddle as we're welding. So it's a manual process. It takes someone to add the filler material into the weld. So every manual welding process is going to be using a constant current power source. So a good way to remember constant current being the power source for shielded metal arc welding is when we're setting up our machines, what's the one major variable that we're changing? It's amperage. Amperage is a synonym for current. So the one setting that you're really changing on your machine is amperage, and that's just a good way to remember that shielded metal arc welding has a constant current power source. Now the other reason why it's important to remember that constant current is the power source for shielded metal arc welding is because as we're welding, as our arc length shortens and gets longer, the voltage varies. It goes up and it goes down, but the current or the amperage relatively stays the same. So I know for some of you who are trying to think, well, if amperage times voltage equals wattage, and wattage is the power of the arc, how does that equal out? Well, the machine does its thing, and so as voltage varies, the amperage stays the same. So that's just another thing to remember, tying constant current to shielded metal arc welding. Now there is another power source out there called constant voltage. So we have two different power sources. One is for manual welding processes. The other is more for wired electrodes. So processes like gas metal arc welding and flux core arc welding, but we'll get into constant voltage a little bit more later. So I'm sure some of you remember the volt ampere curve, where you've got a curve that kind of looks like this, and then you've also got another one that kind of looks like this. So the curve is going to be for constant current, whereas the straight line is more for constant voltage. So before I start throwing too much information out there, let's just go over constant current. So constant current has kind of a drastic drop, a drastic curve. And this is because we need a high amount of voltage in order to start and essentially establish the arc. So when we strike the welding arc, we have a high amount of voltage, and that is just so that way the current can jump the gap from the welding electrode to the base metal. Once we have an arc and the arc stabilizes, we no longer need a high amount of voltage. So over time, and this is like a matter of like a split second, so over time that voltage drops and the machine focuses more on maintaining a constant flow of amperage or constant current. So remember, high voltage just to start and stabilize the welding arc, and then once it stabilizes, it drops down. We don't need as many volts, and now the machine can focus on keeping a constant flow of amps. All right, now let's talk about polarity. So there are two polarities that we need to remember. There's direct current. Let me use a different marker. So there's direct current, and there's also alternating current. Now, two polarities. However, direct current can then be broken down into two subcategories of direct current. There's direct current electrode negative and direct current electrode positive. So when we're choosing the polarity, we either have direct current electrode negative, direct current electrode positive, or alternating current. So now let's take a deeper look at each current and find out some of the characteristics of each polarity. So let's go ahead and let's start with direct current electrode negative. Otherwise known as DCEN. Now there's another term for direct current electrode negative. This is how it was referred to in older times. Some people still refer to it this way today. It is straight polarity. And we'll talk about why it's called straight polarity. But for now, just remember direct current electrode negative is one of the polarities that we can use. So now, when we start looking at direct current and alternating current, the first thing I want to say is direct current, or with direct current, the flow of amperage or the current itself flows in one direction and in one direction only. It flows from negative to the positive. It never changes. So let me go ahead and draw a better illustration for you. Let's say we have our welding machine. All right, we've got, it's gonna say whatever. All right, so we have our welding machine. We have our negative terminal and we have our positive terminal. So if we were to use direct current electrode negative, essentially what that would do is have our negative be connected to the electrode holder, and we would have our positive hooked up to the ground clamp. And so now how the current is going to flow is from negative to positive. So remember, with direct current, the current always flows from negative to the positive. So how that's going to look like is the electrical current starts here at the negative, and it's going to start coming out through the negative cable. Now, as it comes out into the electrode, it's going to enter the base metal. So let me go ahead and actually draw that on here. Let's say we're welding a T-joint, and the T-joint is on a table. And so let me go ahead and just edit this image. That way it looks like the ground clamp is attached to the table. Now, the current is going to continue through the negative cable into the electrode holder, into the electrode, into the welding arc, and then it's going to continue through the table all the way until it reaches the ground clamp. Once it reaches the ground clamp, it's going to continue into the cable. All right, so now we're on the positive side, and it's going to return to the welding machine. So remember, direct current, doesn't matter if it's electrode negative or electrode positive. With direct current, the current always flows from negative to positive. Now, I have the electrode hooked up to the negative terminal because we're on electrode negative. Basically saying that your electrode holder is going to be hooked into the negative terminal. And that leaves only other one location for the ground clamp, the positive terminal. Let's talk about the distribution of heat. So when we have our electrode holder, and we have our electrode, and we have our ground clamp over here, and we have our piece of metal that we're welding on, the electric arc is going to be, obviously putting out heat. Let me make our welding electrode a little bit longer. So that heat is distributed a little unevenly. Now with direct current electrode negative, because the flow of electricity is coming this way from the electrode into the base metal, we are actually pumping the base metal with 2/3 of the heat, which means that the other 1/3 of heat is going to be based at the electrode. So just remember, with DCEN, 2/3 of the heat is going to be focused on the base metal, 1/3 of the heat is going to be on the electrode. All right, now let's talk about direct current electrode positive, or DCEP. Now, just like with direct current electrode negative, there is a nickname for this polarity. Occasionally, you might still hear people refer to it as reverse polarity. Now, that is not to say that the polarity or the flow of current changes directions. It changes directions only in appearance, because now we are hooking the electrode into the positive terminal and the ground clamp to the negative terminal. So while in appearance it may look like the current is changing directions simply because the leads have been swapped, the current is still going from negative to positive. So again, we have our handy dandy welding machine. We have our negative terminal, and we have our positive terminal. So with direct current electrode positive, we're hooking it up just like the name implies, with the electrode hooked into the positive terminal. There's our electrode, and here's our ground clamp. So now the ground clamp is hooked onto the table, and we've got our T-joint that happens to be sitting on the table. Now, like I said, the flow of current does not change directions. It simply changes which cable it goes into first. So starting at the negative, current comes out through the ground clamp cable. It's going to enter the table, and it's going to continue traveling to the workpiece, into the welding arc, and then into the electrode cable, which is hooked into the positive. And then it just returns to the machine. So starts at the negative, goes into the positive. The only thing that changes from DCEN to DCEP is where the ground and the electrode leads are hooked into. So if we have our electrode holder and our electrode, and we have our ground clamp, and we have our T-joint, as our current is flowing from negative to positive, our heat distribution changes again. So with DCEN, 2/3 of the heat was on the base metal. But with DCEP, it reverses. Now we have 1/3 of the heat being focused onto the base plate, and we have the other 2/3 of the heat being focused or placed on the electrode. Now the third polarity is alternating current. Or we can call this AC, alternating current. Now there isn't an old nickname for alternating current, at least none that I'm aware of, being out there in the industry. Now alternating current, things again change a little bit. So with direct current, the current flows in one direction and in one direction only. With alternating current, it actually goes both ways, but it doesn't go both ways simultaneously. It has to go in one direction, stop, and then travel in the other direction. So here we have our welding machine one more time. And it doesn't really matter where the leads are hooked up. So just for sake of illustration, I'm going to go ahead and attach the ground clamp to the negative and the electrode to the positive. Now it's going to be a little weird as I draw this out, so bear with me, okay? So as I said before, the current travels in both directions. Doesn't happen at the same time. It starts at the negative, travels, stops, travels back from the positive. So if that sounds a little confusing, let me go ahead and draw up a different illustration. Okay, so I'm going to show you a graph instead. So let's say the bottom is going to be the negative and the top is going to be the positive. Now, your power is going to start traveling in one direction. So let's say your current starts out at the negative. Now it has to stop. So it's going to peak and then it's going to start coming back down to zero. Actually, let me go ahead and draw that up here, my mistake. So this line represents 0 amps. So whatever you set your machine to, as that current travels out, it's going to peak at the amperage you set it to, and then it's going to start reducing back down to 0 in order to switch to the other polarity. So it's going to start out in one direction. Whatever you set your machine to, that's where it's going to peak at. And then it's going to start reducing down to 0, so that way it could switch polarities. It's like trying to shift your car from drive into reverse. You can, I mean, for all intents and purposes, you can certainly go from drive to reverse, but you're going to do a lot of damage to your car. And so just the same thing with the circuitry of the welding machines. You have to slow down or come back to 0 in order to change directions. So start on negative, get back to 0, and then now the current travels on the other side. And again, it's going to peak out at whatever you set your machine to, and then it's going to start coming back down to 0 before it starts traveling in the other direction. Now, it does this 120 times per second. So it changes direction 120 times per second. So this counts as 1, that counts as 2, and then this would be 3, and then that would be 4. So 120 times a second, or 60 cycles. So one cycle consists of the polarity traveling in one direction, stopping, and then traveling in the next. So this right here is considered one cycle. There are 60 cycles per second. So this isn't really something that we're going to be able to see taking place. Now, if I were to give you the heat distribution, things are a little more balanced with alternating current. So we have 1/2 of the heat is going to be applied to the base material, and the other half is going to be on the electrode. All right, next thing we're going to talk about is duty cycle. Duty cycle, just to keep it short, is the measure of time that you can use your machine consecutively. So if you were just to weld non-stop for a period of time, once you reach this specific period of time, you have to stop and let your machine cool down. So the most common percentage of duty cycle that I keep hearing and keep coming across is 60%. So our first example is going to be with the 60% duty cycle. But before I get too far, let's go ahead and establish the length of time that we have to work with. So typically, or actually always, the length of time that we have to work with is 10 minutes. So that's not to say 10 minutes welding start to finish and then you let it cool off. This 10-minute window is the very beginning of your welding, and then the time that you stop welding, and then the rest of the time that you allow the machine to cool off. So it's always a 10-minute time frame. Now, the other number that we need to take into consideration is the peak output of the machine. So if you have a machine, let's just deal with hypothetical numbers right now. Let's say you have a machine that it's rated for a peak output of 300 amps. So 300 for peak. And let's say that you actually came across a job that required you to weld at 300 amps. Now, if this machine has a 60% duty cycle, that means for 60% of this 10-minute window, you can weld consecutively at 300 amps. So 60% of 10 minutes is 6 minutes. So here's the middle, that's about 5, so around here. So if you were to weld with this machine at 300 amps, which is its peak output, you could weld for 6 minutes non-stop. And then for the other 4 minutes, you would have to let it cool down. Now this is letting it cool down by itself. If you wanted to, say, place a cooling fan next to it, you certainly can do that, but it's not going to reduce the amount of time that you have to wait. You must wait the remainder of this 10-minute window so that way your machine can effectively cool itself off and allow you to weld for the next 10-minute window. Now let's go ahead and let's give a different number. Let's say your machine has a 40% duty cycle. And let's keep all the other numbers the same. So let's say your machine still has a 300 peak output amperage. If you wanted to use the machine to weld at 300 amps, you could. Now, you have to think about this 40%. Welding at 300 amps, 40% of 10 minutes is 4 minutes. So for 4 minutes, you could weld at 300 amps. And for the remaining 6 minutes, you must allow the machine to cool off. Now, every machine has varying duty cycles. There's always going to be one for the highest amount of amperage you could weld at. And let's say you didn't want to weld at 300. Let's say you wanted to weld at 200 amps. Well, your machine is going to have several duty cycles listed in the owner's manual. So if you wanted to weld at 200 amps, you're more than welcome to. The machine is more than capable, but your duty cycle is going to change. So it will be a little higher than what you can weld at its peak output, meaning you can weld for a longer period of time and then let it rest for a shorter period of time. This is all something that changes from welder to welder, and so the only place where you're really going to find this information is in the owner's manual. Okay, now let's talk about electrode classification. So every welding electrode that we come across is going to have a letter and number designation, basically its name. The electrode that we use in this class is an E7018. So by looking at the series of letters and numbers, you can identify a lot of different properties and characteristics about this electrode. Now, you can find these classifications in a couple different ways. You can find them with a 4-digit classification. You can also find them with a 5-digit classification. So let's go ahead, let's start with the 4-digit. We'll break this down and then we'll get to the 5-digit. So starting with the 4-digit, everything stands for something. The E stands for electrode. So what this means is that this electrode not only creates the electric arc, but it also feeds the weld puddle. Now the next two digits, 70, stands for the minimum tensile strength. And this is in KSI. So 70 KSI If you weld with this electrode in the appropriate manner, this weld will hold up to at least 70 KSI before it cracks and breaks. Now, breaking it down from KSI, this would be 70,000 PSI, 70,000 pounds per square inch. So 70 KSI or 70,000 PSI, they're the same. Now the number 1 is telling us what positions we can use this electrode in. Now in this case, the number 1 means all positions. So we can use this electrode in the flat, the horizontal, the vertical, and overhead positions. And then the number 8 tells us the chemical composition of the flux coating. And it also tells us the polarity that we can use with this electrode. Now there's a chart that goes into depth and breaks down all the different types of flux coatings and polarities that each electrode can be used with in the modules. So I'm going to go ahead and keep this short and just stick with this. Now let's move over to the second electrode. So just like with the first, the E stands for electrode. But now we have 5 digits. We don't have 4. So with a 5-digit classification, we're not taking just the first 2, we're taking the first 3 for your tensile strength. So 100 KSI or 100,000 PSI. Now the 2, again, is just telling us the positions that we can use this electrode in. If you find a number 2, this means flat and horizontal only. And then the 4, the last digit, tells us the chemical composition of the flux coating and also the polarity that we can use with this electrode. So you'll come across both out in industry. It's just important to know that with a 4-digit classification, you start with the first 2 digits for the tensile strength. With a 5-digit classification, you start with the first 3. Everything else stays the same. All right, next up are the 5 essentials. You can think of them as the 5 essential variables. They are current, they are travel speed, they are angles, they are electrode diameter, and arc length. These are 5 different variables that we as the welder can change as we're welding. As we change our technique in each one of these essentials, our weld is going to do something different. Our weld is going to potentially look different. So our current, meaning our amperage, if we have a range of amperage that we can use, try to stick within that. If you weld with too low of a current, then your weld is going to be too cold. You're not going to penetrate enough. You're probably going to have lack of fusion. And then just the opposite, if you were to have too high of a current, you'd probably have excessive penetration. You'd be putting in way too much heat into the base metal. There's a lot of problems that can be caused. Just the same with travel speed. If you're traveling too slow, you can add a lot more filler material than what's required. And if you travel too fast, you're taking the risk of not putting in enough filler material. So you're gonna have a lack of reinforcement. And our angles. Now our angles can be broken down into two different angles. There's travel angle. Oh, leave it to me to misspell. And then there's your work angle. Now your travel angle is how you're positioning the electrode in the direction of where you're traveling or away from the direction of travel. So when we start off with basic welds, basic weld joints, I'm right-handed, so I go from left to right. So if I'm using an electrode that requires a drag angle, that means I'm going to be pointing the electrode away from the direction that I'm traveling. A push angle would be pointing the electrode in the direction that I am traveling. Now the work angle is, best way I can describe this is, if you're welding, let's say in a flat position, we already have our travel angle covered. Now the work angle is going to be whether or not we are pointing the electrode towards us or away from us. And this changes when you start getting into vertical. If you're welding vertically, your work angle would be either you're pointing the electrode too far to the left, so the left plate, or too far over to the right plate. You want to keep your electrode balanced right in the root of that joint. So two different angles to think about. And then of course, electrode diameter. If we use a smaller size diameter than what we're used to, we have to remember to change all of these variables that came before. A smaller diameter electrode is going to take much less amperage. It's also going to be changing your travel speed. You might be traveling a little bit faster, a little bit slower, just depending on the job. If you're welding with something with a bigger diameter electrode, it's going to take more current, and again, it's going to change your travel speed. And then your arc length is going to change. So we want to find that sweet spot within one diameter of the electrode. So if you're welding with a 1/8 inch diameter electrode, you want there to be approximately 1/8 of an inch between the tip of the electrode and the weld. As you increase your arc length, you are increasing the resistance to the flow of current. And it's also going to do a couple other things. Just the same where if your arc length is too short, you take a risk of sticking the electrode, but then some other things can happen too. So these are 5 things that we as a welder can control. I know sometimes our machines do things that we don't want them to, but at the end of the day, these are 5 things that we can control. Now let's get started on welding joints. So there are 5 common welding joints. The most common, the one that we've been using in our class the most, is the T-joint. You might also see it spelled all the way out, T-E-E joint. Either way, doesn't really matter. Then we also have our lap joint. We have our corner joint. We have our butt joint. And we have our edge joint. That's probably as far as I'm going to get into the joints. There are pictures of these in previous lectures and even a handout, so make sure to reference those. But just remember, these are the 5 common welding joints. Anything that you do out in industry is going to be a variation of one of these 5 joints. So I guess I can draw these out just really quick, but I won't get into too many examples. Your T-joint, the most common form that we've seen this in is with one plate laying flat on the table and one plate being placed on top of that, perpendicular, to where it forms an inverted T. Now the lap joint is where you take, again, 2 plates, lay them against each other in a way that there is some overlap. The corner joint is where you have 2 plates that when they come together, they form a corner. Your butt joint is where 2 plates are essentially flat for this example, and they are butted up against their edges. Now the edge joint can sometimes be confused for the butt joint. An edge joint is where 2 plates are fitted against each other on their faces, and they are welded along their edge. So right here or right here. All right, next let's talk about welding positions. Now, we're only going to be talking about 4 welding positions in this course. There are more, but we're only focusing on 4 just to get the foundation that we need. They are flat, horizontal, vertical, and overhead. So we've done flat, we've done horizontal, and we've done vertical in the shop. We have not done overhead. We're saving that for the more advanced courses. For now, in this course, we're only focusing on the first 3 with our lab projects. So to take this even further, there is a number designation that's given to each position. So similar to welding electrodes having their own classification, there's something similar for positions. So flat is identified by the number 1. Horizontal is identified by the number 2. Vertical is 3 and overhead is 4. Now something I realized that I missed, and so let me backtrack really quick. Vertical. Everything that we do in this course is going to be vertical uphill, starting from the bottom, welding to the top. There will be times where you find yourself welding vertical down, starting at the top and welding to the bottom. However, those are very specific situations. So if you ever hear someone say vertical or just weld this in the vertical position, always assume vertical up. You will need to be specifically told vertical down, and we'll get into those reasons at another time. Now, with the numbers being splayed out, there is something else that needs to be added to it. This is where we start coming across fillet welds and groove welds. So depending on the type of weld you're creating, you're going to find something else being added. You're going to find a letter. Now, in case of a fillet weld, a flat fillet would be identified as a 1F. A horizontal fillet would be identified as a 2F. A vertical fillet, 3F, and a 4F for an overhead fillet. Now, follow the pattern. With a groove weld, a flat groove would be a 1G. Horizontal groove would be a 2G. All right, and then 3G and 4G. So if you ever hear someone say this joint needs to be a 2G, remember 2 means horizontal and G means groove. Just the same if someone were to say, hey, this weld needs to be a 4F. Remember, overhead is identified by the number 4. Fillet is identified by the letter F. So a 4F would mean an overhead fillet. All right, now let's talk about weld symbols. So whenever we're reading blueprints, we're always going to be given some type of welding symbol that gives us information on how to prepare the metal and how to deposit the weld. It all starts with something called the reference line. Here we have the basis for the reference line. It's just a straight line across. Now you'll also see the reference line attached to a broken line with an arrow at the tip. This can be called the leader line, it could be called the arrowhead line, the pointer line. I've heard it called many different things, but at the end, this is just, I like to say this is the leader line that's attached to the reference line. Now the third part of the reference line is going to be the tail section. So a complete reference line could look like this. One thing that I'll get into later on is that the tail section is actually optional. If there's nothing that needs to be conveyed to the welder that would typically go in the tail section, then it's actually just excluded from the blueprint. Now let's talk about something called side significance. You're going to see weld symbols placed either on top of the reference line or underneath the reference line. This is where things, if we don't pay attention, we can get really tripped up and we can actually ruin a project. So anything that is on top of the reference line is called other side. Everything that's underneath the reference line is called arrow side. One thing that I want to point out here is that side significance never changes. Never changes. So let's say instead of the arrow pointing down, let's say it's pointing up. Just because the arrow is now pointing up doesn't mean that side significance changes. It stays the same. And just the same where if the reference line were instead pointing to the left, side significance stays the same. If it's written on top, it will always be other side. If it's written on bottom, it will always be arrow side. Now if you're saying to yourself, well, that's cool, other side, arrow side, but what does that even mean? Let's say, let me go ahead and erase this. And let's start with an example. Let's give you the weld symbol for a fillet weld. That's the symbol for the fillet weld. And now if I were to say deposit this fillet weld on a T-joint, where would that fillet weld go? So with the fillet weld being on the arrow side, all we need to do is simply follow the arrow and look at what joint is being pointed to. this fillet weld is going to be deposited in the joint that the arrow points to. So it's pointing to this side of the T-joint, which means that the fillet weld is going to go right there. Now what happens if instead we get a fillet weld on the other side? Somewhat similar concept. We figure out where the arrow is pointing to. The arrow is pointing to this side of the joint. So if it's on the other side, we simply find the joint opposite to here, which would be this location. So follow the arrow, see where it's pointing to, and then jump to the other side. Whereas arrow side is basically place the weld where the arrow points to. Now there are a lot of there are a lot of different weld symbols out there. So let me go ahead and just draw a reference line up. So we have already established that this symbol is the symbol for a fillet weld. Now groove welds get a little bit more complicated. You might see something that looks like an open V. You could see something that looks like a slightly closed V. You could see something that looks like this, and so on and so forth. So without going too far into detail with each of the different groove weld symbols, I just want to leave you with this additional piece for the reference line. If you were to see a weld symbol for a single bevel, you could see this arrow line do something different. You could see it with an additional break. So you could see something like that. Now, whenever you see a break, it's because when we start getting into groove welds, we need to prepare the edges of our material a little differently. And so the arrow is going to tell you which plate needs to be prepared. Now this only comes into play when you have stuff like a single bevel, a single J, things of that nature. So if you have a single bevel and you have two plates, the arrow is going to tell you which plate is being beveled. So because it's other side and the arrow is pointing to this plate is going to be the one that receives the bevel. But because it's on other side, and actually let me draw this plate up a little bit bigger. So because it's on other side, that means the bevel is going to be located here. Just like that. Now if the bevel were on the bottom side, or the arrow side, the arrow still points to this plate. But now instead of the plate being beveled down here, it's going to be beveled like this.